All right, we're going to get started. Good morning, good afternoon, good evening, everyone. My name is Lindsay Florian, and I'm an associate scientist here at Pumas AI. I am joined today by Dr. Chris Alrod, our Associate Director of Engineering Research, and Jose Storali, our Lead of Training and Education. And today we are going to talk about SAEM in Pumas. If you are not, I apologize. If you're not familiar with our company, here at Pumas AI, we engineer solutions to empower those in the front lines of healthcare from drug discovery to delivery. We have two main products, Pumas, which is our accelerated drug development software, and Live, which is also a clinical decision support software that's currently being used in hospitals around the world. However, today we're just going to focus on Pumas. It is, as I said, our accelerated drug development software. It is the fastest end-to-end pharmaceutical modeling and simulation platform for quantitative analysis across the drug development lifecycle. And here are a few key points about Pumas that I'd like to highlight. Pumas is a software that has been validated against other industry softwares and is comparable or even better in certain circumstances. We are a one-stop shop, meaning that you can do your data wrangling, plotting, simulation, and reporting all in one software. Submissions using Pumas are accepted by the US FDA and have been approved. We are also super fast because we utilize Julia, which is high performance computing, and we are sometimes much faster than our competitors, up to 300 times. And one other highlight I would like to bring to forth is we can do scientific machine learning. One of our future endeavors that should be coming out soon is Deep Pumas, and hopefully we will have more information for you in the near future. So with that, I would like to hand this presentation over to Dr. Chris Alrod, who will give you a brief summary about SAEM, followed by a live demo by Dr. Jose Storali. And so, Chris, feel free to share.
All right, I am looking for
the share screen button.
Yeah, there we go.
Yeah.
All right.
Oh, hang on. I think we are seeing like an empty white horizontal line.
Oh, well, that was sharing the
PDF.
I guess I would try sharing my entire desktop then. I was trying to share the, can you see it now?
Yes, we can see it. Slide
All right.
12.
I was sharing Firefox, but Firefox was in presentation mode. So I guess Firefox was, I don't know, well, whatever. I guess, so now we have it. Okay, so, I mean, first I'll just introduce everyone to, I guess, the traditional EM algorithm, but also the point, of course, of algorithms like, FOCE and Laplace I in Pumas is that you want to estimate the marginal likelihood. We have these models where we have a lot of random effects, which we represent here by eta, that we consider to be nuisance parameters and therefore are not particularly interested in estimating or the estimates of. Instead, we have just some population parameters that we would like to estimate. For example, you might have like some population clearance level or like some average clearance level, and then every individual within the population, it has some distribution centered or parametrized by that, and those individual values are what we would like to sort of integrate out to get the marginalized log likelihood of only the parameter values themselves. Now, while techniques like FOC and Laplace I give us a approximation to the log likelihood, the EM algorithm actually would let us estimate the maximum of the exact log likelihood. Now it works iteratively through defining a function as, so iteratively through defining a function that gives us the expectation of the full log likelihood. Here, this means I get the product of these two terms, the joint, and then we maximize it and to define the parameters of the next iteration. So then, once we have these updated parameters, we again get define this expectation function, and we keep repeating. So some strengths are that it, like as I just said, it converges to the exact answer rather than some approximation. It is also general. It requires few assumptions. So unlike, for example, FOSS, where we do not support that for time to event models, for example, or if you have something like, I don't know, a t distribution as your error model, right? The EM algorithm is much more generic. And should I look at questions? Okay. Yeah. So, and in certain models, particularly if you have exponential family, you might be able to define closed form solutions for both steps, which of course would make the algorithm fast. Unfortunately, in reality, our models tend to never be in the exponential family. They tend to be much more, well, I mean, A, they tend to be much more complicated, and B, you probably don't necessarily, as your workflow, want to spend time then studying and analyzing the particular distribution you created to find out all of its statistical properties. You want to get estimates for the model that you're stitching together. But I mean, with dynamics like an ODE system in there, odds are it's not going to happen. I mean, things as simple as the t distribution in Pareto are not exponential families. So, but anyways, getting into the weaknesses of the traditional EM is that one of them is that it converges only to a local optima rather than the global optima. So if you have a multimodal distribution, you might not find actually the global mode, just the closest mode. And of course, there are ways to work around this, such as multiple starts. Like if you initialize a bunch of different random parameter values and run the EM algorithm, and on each of them, you can then pick whichever mode led to the largest log likelihood. You can do things like randomly perturbing parameters to see if you can jostle them out. But that's a difficulty there. Additionally, approximating the function for the expectation step can be expensive. You can, for example, if you how are you, I guess, performing that step? One way you can do it would be through Monte Carlo. So for each expectation step, you draw a bunch of MCMC samples and enough of them to try and get maybe the variability of it down. I mean, that can then be very computationally intensive, and then that would also lead to a expensive maximization step if your log likelihood is now sort of the mean of all of these samples. Now you have a whole lot more computation to be doing in the maximization step. You could also, of course, use numerical integration, but that doesn't scale to more than just a small number of dimensions. And then you would also probably need to be running that inside your maximizer as well. So that can lead to bad performance, both in the runtime as well as maybe not converging to a global mode. So, I mean, there's of course a lot of different flavors of the EM algorithm. Many of them, taking some approach to try and address these issues. And perhaps the most popular of these varieties is SAEM, or stochastic approximation expectation maximization. So, just as quick overview and in reference to the previous side, the stochastic nature of it helps it, better find the global maxima, because it tends to, particularly in the early stages of the algorithm running, jump around a lot, which helps it escape the global maxima. And you can also, escape the local maxima to find the global maxima. And it also tends to incorporate a simulated annealing, which it does by a flattening of the log likelihood to also help with this, so that the jumps out of the local ones are easier. And it also makes the expectation maximization steps very cheap. In our implementation in Pumas, the expectation step involves drawing and keeping a single sample, although that sample might require many different transitions. What I mean by that, well, is sort of like thinning. It tries to, based on the current step size, it will take a variable number of steps before it settles on a sample that it uses for the next iteration. And that's just so that we can try and cut down on autocorrelation between these samples. Because the maximization step still has costs, so it's not necessarily worth it to have a maximization step every time. Instead, we might take 10 steps, for example, and a step could be 0, if we reject, right? So we have 10 proposals or so, and that's adaptive. It can be up to 100 before we go to a maximization step. The maximization step has to happen serially, while the expectation step can of course happen in parallel. But if you have 100 subjects and 10 cores, then you can divide up these subjects among cores for the expectation step, and then you calculate some summary statistics and then send them to a single the primary worker for the maximization step, which in SAEM, you just update some sufficient statistics and use these sufficient statistics to calculate your parameter values, so that it makes the maximization step very cheap. It also does not require any gradients, unlike FOCE or Laplace I, which to get gradients with respect to those algorithms. So those algorithms themselves need gradients. Like Laplace I needs second derivatives, FOCE needs first derivatives for the approximate log likelihood themselves. And then for the fitting process of fitting these, where you need gradients with respect to those log likelihoods to improve your parameter estimates, you now suddenly need second derivatives for FOCE and third derivatives for Laplace I, while SAM does not need these derivatives. It doesn't need them at all for most parameters, and it does, however, need them if you have an error model that is not the additive or proportional normal. But then it only needs to take these derivatives with respect to the variability parameters of your error model. So it does not actually then have to sort of take the derivative with respect to most of the likelihood. It only takes it with conditional on the rest of the parameters. So that is a much, much smaller function and much fewer parameters. So it's computationally much lighter than these other methods, at least with respect, in some respects. So let's get a little more into then how SCM works. So basically we have, for each iteration, we want to draw samples of our random effects. And then we use these random effects to update sufficient statistics that we have for all of our parameters in the model, which includes both like the variability parameters of our error model, of the random effects themselves, as well as of parameters that are let us compute the expectation. And then yeah, and those solutions can be used to update the parameter estimates, which then leads us to the next iteration where we use these updated parameter estimates. So as a comment when I say like parameters leading to expectation, so a limitation, which I'll talk about a little more a few slides after this, is that the random effects, a restriction is that they do have to be normal. And when I say parameters leading expectation, you are allowed to have basically linear models as the means of your normal model. So, and this is also how all parameters do have to be estimated from either this or from the error model itself. So, if you have, I mean, as an example, you could have CL is normally distributed with mean mu plus beta times X. Then you would estimate the omega associated with this, as well as this one random effect would let you estimate both that mu and beta term. If you want to have parameters without any associated random effect, like if your model has just a population parameter by itself, then then the algorithm currently works via having it just have a mean parameter and also, the associated omega, but then through the course of sampling, at first it samples normally so that this can be highly variable, but then as we move into the later iterations, we start driving down the omega towards 0 to try and turn that parameter into a relative constant. So that's a bit less efficient, but still then a way to be able to use parameters. Ideally, you can try and get as many of parameters as you can into these sort of linear systems, like the mu plus beta plus, you can have as many terms there as you want, but these have to be linear, and the x's are not allowed to be time varying when used within these formulas. I think Jose may go into that a little more with some of his demos. So that should be, I guess I can now, I'll move on to some more details on some of the parameters that you can use to adjust the sampling behavior within Pumas. One is that there is a keyword argument to the pumas.sem called alpha, and it's bounded between 0 and 1. So basically the weight placed on an iteration decreases across iterations at a rate of s to the negative alpha power. So what that means is, as we update our old parameter estimates, we decrease the weight of each new iteration by a certain amount. If we take alpha equals 1, then the rate at which we decrease the value of our new iterations leads us to essentially place even weight on all iterations. I mean, you can of course think of it that well, when you're taking the average of 3, then you're adding a fourth term. That fourth term has to have a weight of 1/4. Right, so then you need s to the -1, right, for the -1, right, and then on the 10th iteration you would need 1/10. But it is often early on profitable to place actually much more weight than this on the most recent iteration. So in the first stages of SAM fitting, we actually use alpha equals 0, which means we place all of the weight on the most recent iteration and totally discard all previous information. So that allows SEM to jump around rapidly. And I mean, you can also think of it like for the first iterations where the model hasn't converged and you just have an initial value, you don't want to keep that history around sort of influencing the parameter estimates. You want to instead be, I guess, randomly exploring the space, hopefully finding the region of the true mode. And then we transition to a step with alpha of 0.7, where it begins to, from there, converge towards, and keep the history starting from there towards the true mode, before finally trying to smooth out by placing even weight on all of the iterations. So another thing to emphasize is I'd mentioned simulated annealing before, which where we flatten the likelihood. That is done through inflating the omega and sigma values. Now, that's also something important to keep in mind as a practitioner using SAM, is that we do this inflation by sort of setting the omega's initial values to the identity matrix and the variability parameters, which for a normal distribution would mean the standard deviation parameters. But I use the word variability because we support a lot of different distributions that where their most natural parameters may not correspond to the standard deviations. Although you should try to have them do so. Actually, maybe we do that. Anyway, so we pin them to 1, or not pin them, we initialize them to 1, and then they do get updated as we sample. However, they get updated much more slowly. We have this lambda argument to SAM, and they're and on each iteration, the estimate for these parameters is set to basically the maximum of the estimate and lambda times the previous estimate. So lambda defaults to 0.975. So that would mean if the estimate after one iteration is 0.1, and it is initialized to the value of 1, then the maximum is 0.975, many times larger than that 0.1. So that causes a rather slow descent of these parameters to the true values. Having very large omegas and very sigmas is important because the flattening of the likelihood is necessary for the parameter to actually be able to jump around rapidly across the distribution. Right, this is so that it can find the area of the hopefully the global maxima and converge there. So the reason emphasizing this is that if you do not specify these parameters in your nits, they do default to 1. If you do specify them, I mean, it is a mistake I've seen before of somebody specifying them with, oh, I believe it to be about 0.1. So they think they're helping by specifying it as approximately, the value they believe it to be, which, even if they're correct, will yield much worse model performance or much worse performance of the SAM algorithm than by using the inflated value. So always insert something. Oh, well, always either leave it uninitialized if you think the value is much less than 1, or initialize it to be something greater. On the other hand, do keep in mind that that it can only decrease at the rate of this lambda per iteration. So if you set it to 1 trillion, then the likelihood would sort of still be flat probably by the time you're done sampling. So you do need to allow it to actually converge to the correct values. So you would want this rate of descent to be able to achieve the true values before the end. So on restrictions, I had already covered these earlier. So I'll go into these code snippets before I guess Jose really walks you through. the thing to emphasize is in translating, this I was just wanting to sort of repeat what I had said on restrictions before. So when we had that Pumas model, you might naively try and translate it like literally into the Pumas model of saying, okay, you have this ADA, you have this TVCL, and then you still have, you know, written like this to just be like the most straightforward translation that you can. However, this is not actually equivalent to the previous model in that this ADA has a mean. This is not a zero mean number. So we're actually estimating two mean parameters here, which makes this model non-identifiable. And non-identifiable models tend not to fit well. Of course, plus, you know, not being interpretable, you're like, it just, since, I mean, you can arbitrarily increase the mean of this and decrease the mean of the ADA. So the correct way to specify that in Pumas would be, or into the Pumas EM model, is just to say CL1 normal. Oh, sorry, this should have been log normal. That was my mistake. So with log normal, that would have been equivalent here, or we can say log CL and then exponentiate it down here, but I would just do log normal. And when I say only normal distributions are supported, transformations of normal distributions are, for all intents and purposes, essentially normal. And so when we have log normal, we have a normal essentially with linear, and you can have, you know, still the linear terms such as mu plus beta times x, and then that just gets exponentiated, which is afterwards to produce the log normal distribution. And that also, of course, means the linear terms do then sort of have a multiplicative effect once we do that as well. But, you know, it's worth keep in mind that you still have, you know, log normal and logit normal support. But are there any questions, or should I go ahead and hand it over to Jose?
So if anyone has questions about the theoretical part of things that Chris exposed, feel free to ask in the chat, or you can also ask questions later after the code demonstration. Okay, so let's go to the coding part. I'm gonna share my screen. And
Should I
Chris
stop?
needs to stop. Yeah, otherwise I cannot. Thank you. Are you guys seeing my screen?
Yep.
Okay, so let me change that to another theme, light theme. I go, it's better for everyone. So SAM, it's contained in the Pumas package. So for us to use SAM, we just do using Pumas. And for our demonstration purpose, I'm using a package that you should have access in your Pumas IDE called Pharma Datasets. And I'm using a standard, so let's load these packages. I'm using a standard IV, one compartment model. So it's a simple model. And this is the data set. So IVST. So as you can see, we have 120 subjects. We have a time variable, a concentration variable, a CP variable, a concentration variable, which is named as DV, dependent variable, amount, EVID, so if it's a measurement event or a dosing event, and the compartment, since it's a one compartment model, it's all a column filled with ones. Also the rate, since it's a bolus, the rate is 0, and a dose group, which could be a covariate in our study, but in this model, we are not using any covariates, but the data set has a covariate. So as you define the SAM model, you use the macro EM model, not the macro model. So in Pumas, you do something like model. And in SAM, as Chris specified, you use EM model. That's expectation maximization model. And we start with our model block. So as Chris described it, in order for a model to be identifiable, this simple one compartment IV model, we only need a random block. So our block is pretty much, we have a CL and a clearance PK parameter and a volume of distribution PK parameter. So both of those, we use this formula syntax here, which is very conventional for people that comes from the R world. The R formulas from non-linear and linear models, either mixed or non-mixed models. So this means that you only have one intercept for the CL. So it's pretty much like a single parameter here. And this is distributed as a log normal, both the PK parameters, the clearance and the volume of distribution. So that's how we specify. We also specify an at covariance to say that our covariance matrix for the random facts is size 2 by 2. So that's how we do it. Our model is a simple one compartment IV model. We do have an analytical closed form solution. It's central one, but we could also do something like this. If you want to, we can also do something like this. It will be the same. Pumas will make a check under the hood, and we'll see that this OD is linear, so it will use a closed form solution. And so it's pretty much the same, but we can use this keyword here, central one, which is pretty much one compartment, central model, IV model. We have all of those in the Pumas documentation. Then we have post and pre. Here we don't have any pre-computations, but we do have a post computation where we scale back our concentration to the specified units. So here the units, I think it's I'm gonna butcher the units, but we do need to scale them by 1,000 because it's milligram per deciliter maybe, and we need grams per liter, something like this. Maybe Lindsay can correct me if I'm wrong, but we do need to scale the concentration for our units of our PK parameters. So that's why we multiply by 1,000. And then our error, our dependent variable, dv, is distributed as a proportional normal with mean CP. So it's a little bit different from the Pumas approximate likelihood models like FOC or Laplace I models, but the idea is pretty much the same. So this is our model, a simple model. We specify our initial parameters estimates pretty much once. So as Chris said, my needs are not, it doesn't need to be closer to the real estimates like we need to do in the FOCE estimation methods. If we specify needs close to our real parameter values, maybe we are hampering our fit procedure. So that's why I'm pretty much initializing all of those to 1. And now we fit our one compartment model using the fit function. It's the same signature as Puma. As Puma's, the first position argument is your model, population, your parameters, your set of initial parameters. Then in the fourth position argument, you would generally put something like Puma's FOCE here, but now we are using SAM. So that's Puma's SAM. And if you take a look at the documentation, you see that we have an ithers keyword argument. This is a tuple of size 3, indicate the number of iterations that you would run in the 3 phases of the SAM estimation. So the first phase is called the exploratory. The second phase is called the middle and the smoothing. And Chris described that with the alphas in his slide, I think slide 7 maybe. And here, since it's a simple model, the exploration phase is 200, like the default, but the middle and the smoothing phase, I'm using 1,000. So when we run this, if I hit the right things, it will take a while and it will print our estimates after that. And why it's erroring? Oh boy. Okay, this is why. Let me try again. Yeah, I don't know what's erroring here. Oh, the population. Sorry about that. I need to specify the population. I had another population. Now it will run. Live coding is sometimes you can shoot yourself in the foot. So it takes some time to run because we changed the default middle and smoothing phases from 100 iterations to 1,000. And in a couple seconds, we should see our results, our estimation results. Actually, just one correction, only omegas and sigmas should be closer to 1. The other ones can be close to the real estimate. And you would speed up. So these PK parameters I can put, it needs like close to 3.9 and 15 respectively. And this should speed up our model. So that's simple example. Now let's do something more fancy. So I have another file here called SAM2 time varying. And I'm just gonna run this because it takes a while to run. And then I'm gonna explain the code while it's running. So let's close this. Okay, let's close this. So now we are doing an ordinal regression. So this is a data set called pain remedy. It's we do have an ordinal data set. We have a PK model, but our dependent variable is a pain scale in a scale from 1 to 4, I guess. Yeah, 1 to 4. So actually it's 0, 1, 2, 3, but we in a scale from 0 to 3, that how much pain are you experiencing now? So that's our dependent variable. So we are in an ordinal regression problem. And we read our data set, this return our data frame. So as you can see, we have ID here, and we have 160 subjects. We have the arm here for which arm of the oops, which arm of the experiment they are. We also have the dose, time, concentration, and the pain ord. So the pain ord is our dependent variable. So it's the scale of pain. So take a look at this poor fellow here. He's in the pretty much in the time equals 0. So his pain is 3, very high. Then it kind of decreases, and as the concentration keeps getting lower, his pain is coming back again. So 0, 1, 2. So that's pretty much our data set. Then we read our population with the read pumas. It's the same population. Now this model, as I said, has a time varying covariate. Some solutions, despite being industry standard, some competitors, they cannot tolerate time varying covariates. We do. So one more argument for you to use Pumas, it's easier to use, it's faster, and also you can do time varying covariates, really easy. So here is our ordinal SAM model. So we do have some parameters here. This B1, B2, B3, they are our cut points in the ordinal regression. So ordinal regression, we cannot model this pane ord, these interval ordinal variables with a linear regression because we do not have the assumption of equal distance. So the distance from 0 to 1 is not the same from 1 to 2, and it's not the same from 2 to 3. So that's why we cannot do linear regression. We need to violate the equidistant assumption of the linear regression, the metric assumption also called. So that's why we use these cut points. And by default, we need k-1 cut points. So if we have four unique values, we have 0, 1, 2, 3. So we pretty much need only 3 cut points. So that's why you have B1, 2, 3. The parameters here, we have a slope in our parameters. For the random, we have the B1. And we pretty much specify our time varying covariate here. We calculate an effect, which is pretty much our time covariant times the slope, which is in our parameter block. And we do the logit of the cumulative probability. So this is pretty much our log cumulative odds. That's how we do it. Then we do the logistic regression for the probabilities of greater than E0. And this is pretty much our log, our cumulative probabilities of the cutoff points, so higher or equal than 0, 1, and 2. And we don't have higher and equal than 3 because that's the maximum point. So that's why we need k-1 cut points or intercepts in this model. And our dependent variable is the pane ord and is distributed as a categorical where we pretty much construct from our cumulative probabilities the discrete probabilities as the k-1 minus the probability of k. So our P0 is pretty much the probability of being higher than 2 than 2. So that's pretty much is 1 minus this probability. And then we keep going, constructing our probabilities from the cumulative probabilities of our cut points. And we pretty much put all of those into a categorical distribution. This distribution has the assumption that all of the p's here, they sum up to 1, and they are ordered. So P0 is less than P1, less than P2, and less than P3. And that's our model. We have some initial parameters estimates, and here is our SAM. As before, we call the fit model. First position argument, second position argument is population. Third position argument is our set of parameters, our initial estimates. And then we call our estimation method, in this case is SAM. But now my ithers, the exploration phase, since this is a more complicated model, I'm giving 2000 iterations so that it can explore a lot of the sample space. And the middle and the smoothing phase are again 1000. And this gives back our slope and our cutoff points, so beta B1, B2, B3, and also gives our random effect. So we do have 1 omega here, which is the B1 here. So that's how we do it. So here's an example with a time varying covariate. There's a lot of going on because it's an ordinal regression, so we do need to have a lot of pre-computations here. Pretty much this whole block here. So let me take this out. So this whole block here in the pre-block is just to calculate those cut points. If you had something like a linear regression or something like a dependent variable that is linear and you don't need to calculate any of this, your pre-block would be pretty much your independent variable, your time varying covariates times the slope. So it will be just a one-liner. But here we do have to do a lot of pre-computations of the cut points to get back. So that's the idea here. This model takes around 2 minutes to fit, so it's pretty fast. And the estimates are pretty good. If you run the same model in Pumas using a first order conditional estimation, FOCE, the estimates are pretty much the same. So we have pretty much the same estimates. I guess that's it for coding. I have a simple example, one compartment model, and we have the time varying covariates because it's something that we can do it, and other solutions or other competitors that are established as notorious Saem estimation software cannot do time varying covariates. So that's one thing that I wanted to showcase today for you. Let me see if we have questions in the chat. Okay, we do have some great questions. So let me let me start. Let me keep sharing my screen because maybe we need to type in some things. So we do have some questions. Hihani asks us, can you please give us more examples on when to use SAME versus others estimation methods? I don't know if Chris wants to chime in this question.
So I'm not totally, so I think that's, well, it's hard for me to say honestly. I mean, one thing I would say is, of course, that if you have error models that FOSS does not support, that's a good reason to try to use SAM. If you're also concerned about the approximation involved in FOSS, then that's also perhaps another reason to consider SAM. It is, I mean, hopefully the answers compare, so are comparable, but I mean, it's probably then highly model dependent. Also, I'd like to respond to Daria to the SAM fit method accepts a vector of random number generators. So that is how I would suggest controlling the seeds.
Where do I pass it?
The fit method.
Oh, the fit method. Okay.
Yeah. So, and when you do a vector of them, the length of this vector determines the number of threads that run in parallel. So if your vector is of length, 8, then it will run 8 in parallel. That will also override anything else. So if your vector is of length 100 and you have a 4-core system, it will try to, and you have enough subjects, it will try and split it up into the 100 because it will want you to be able to get the same answer wherever you move your computation to favor reproducibility. So you will control how many separate, things run in parallel through the length of that vector.
So RNG, and then I pass a vector of I don't
So-
know, percent twister something. Could be a non-thread safe, because each one of the threads will get its own random number generator seed, right?
Yeah. I mean, that's why you need one RNG per thread is so that, I mean, thread safety, I guess, is one concern, but another is that, of course, the order that different things run or that different threads run is not guaranteed by anything, right? So you want you to have the same sequence every single time you run it, which means that, so the easiest way to do that is to just give every thread their own RNG, because RNG1, the order, it might be called, like, one time that you run a fit, rand could be
Like
called,
this, right?
that I would not do fill, because fill will set the same RNG everywhere, and now every thread gets the same sequence.
Just to showcase it, but this would be something like, you can do something like this. So
do like map
RNG,
or like that. Yeah.
I, and then travel.
There is also,
I.
if you want to use Mersenne Twister, you could also do using future.
No, let's not complicate it. What is the default one? I forgot.
The default RNG starts with an X. Soshiro.
Oh, Shoshiro. That's it.
And hopefully that is also how you initialize it. I can double check locally. Yeah.
So 1 to 8. There you go.
Yeah. So like thread 1 might call, the number, its own random number generator twice before thread 2 ever does the first time. And then the next time you run it, it might be the other way around. So you need each to have their own. So that way, the calls to each random number generator are always in fixed sequence, regardless of what the order of things actually running on the threads are, because that could be variable. And so actually, SAEM will not run in parallel by default. So odds are this will also run faster.
Oh, really?
The SAEM doesn't have a closing parentheses. Iters closes, but then no. There we go.
Yeah, thank you. While this runs, I also want to tackle the question from the when to use it. So there is a philosophical also argument. So FOCE is an approximation. SAM is it's guaranteed that asymptotically, if you have all the time in the universe, and you would converge to the true distribution, to the true underlying distribution of your parameters. So one approximates, the other one is an approximation to the ground truth. The other one is an approximation. So there is this also philosophical argument. But sometimes the question is best answered, I pretty much, if my team or my supervisor, my boss, is familiar with SAM or not, this is pretty much the answer that you need to be asking if you want to use SAM or not. Or if you are in a good environment, a healthy one, you can introduce SAM as, why don't we take a look at this new estimation method that we never use it? So that might be a nice change of things. It depends really on what you want to achieve. Yeah, there is this philosophical argument that it's an approximation of the ground truth.
So in initializing these random number generator sequences, I think in Pumas, we will add we will make it be multi-threaded by default, and we will probably expose some functionality for setting the sequences far apart, meaning like the Soshiro has 256 bits of state, so it would have sequences of 2 to the 256 before repeating. So, and it is possible to jump ahead certain numbers. So we could have a jump ahead function that creates, then an evenly spaced one. So if we make 8, then we could have them each be like 2 to the 48, spaces apart from each other. That way you would need to sample 2 to the 248th power times before any of them overlap with each other. And that is, well, odds are, I mean, as you can guess from the magnitude of that number, just picking things at random is still going to land you far enough apart that you're never in practice going to, but peace of mind, I guess.
Yeah, so let's get back to Lindsay for the closing remarks.
Well, as we just finished running the example, thank you everyone for joining today. If you think of any other questions after this webinar has ended, please feel free to post them on discourse.pumas.ai, community for Pumas questions. This webinar will be posted with code and slides on Pumas Labs later this week, so please keep an eye out for that. And our next webinar will be parametric time to event models on August 2nd at this exact same time. We are postponing it by 1 week because the last week of July is JuliaCon, so feel free to check out those talks as well. And with that.
Yeah, and also, sorry to interrupt. JuliaCon will be very nice. We do have a keynote speaker. It's Hussein from Moderna. He will be speaking about how he uses Julia and Pumas in Moderna to pretty much have a very intuitive, easy to use, fast, and stack of tools based on Julia and Pumas. Sorry to interrupt you, Lindsay.
No, it's okay.
I'm also giving a short 8-minute lightning talk about simple chains, which is one of the tools that's a part of the upcoming Deep Pumas.
And also, one last thing, if you want to know more about Julia, the first pre-workshop will be an introduction to Julia from very beginners. And I will be doing the pre-workshop. So feel free to join in to know more about Julia.
So with that, we look forward to seeing you at any of these events and talks upcoming, and as well as hopefully our next webinar. I'm going to stop the recording now, and we will stick around for a few minutes if you have any other questions. But with that, have a great morning, afternoon, evening, wherever you are.